Welcome to Faith and Science. I'm Dr. John Ashton. Most of us are familiar with the organic produce section in the supermarket or in country markets, and we just accept it. But my understanding is that the whole concept of organic gardening was started by a former professor of agriculture at the University of Oxford, Sir Albert Howard. And I remember, and he wrote an interesting book called An Agricultural Testament. And his thesis was essentially that, particularly by mulching around plants and putting in a lot of dead vegetable matter, that encouraged the development of fungi, and as plants protected themselves against the fungi, they developed or produced compounds that were quite beneficial for our health. And also, though, one of the other things that I remember reading that he said was that insects are the true professors of agriculture. So his whole idea was that the role of insects was to remove the weaker plants from the system so that the stronger plants continued on and remove diseased plants and so forth. It's very, very interesting concept. And then, of course, he said insects are controlled by the warfare that they conduct amongst themselves, and so this stops the insects from sort of just getting out of control and I guess taking over and eating everything. And of course, one of the roles or one of the types of areas that this fits into, of course, is spiders. And though perhaps spiders aren't truly an insect, but they're a slightly different class of animals. But it's interesting that they play a major role in regulating the level of insects. Now, of course, some people say, well, look, this is a major problem for the whole concept of creation. So were there venomous spiders before the fall? And because we know that in the beginning God created everything, it was very good. And there was, we don't believe that there was any suffering or death before the fall. But how could, this be? What about, bacteria? Obviously, if we have food, there are bacteria die. And at the present time, and then bacteria, if all the bacteria kept breeding and living, things would take over. And we know again that viruses help regulate and control the level of bacteria. And so there are all these things here. But when we think about spiders injecting venom from well-designed glands into their prey to kill and eat them, did these things happen? So it's an interesting problem from the creationist view but one of the particular things is that this whole concept of death seems to be restricted to the death of truly sentient creatures, that is, creatures capable of suffering, such as vertebrates. So plants and bacteria, etc., are not alive in the sense that they seem to be able to sense suffering, although some people, sort of dispute this. But, for example, a dragonfly is capable of calmly eating its own abdomen. So they don't. So insects and invertebrates such as spiders and this sort of thing don't seem to experience pain, and also they they don't sort of raise things as a family. They lay eggs. Those eggs hatch quite independently. So it's almost like they're little machines, little self-replicating machines. They have a function in maintaining the environment. And it seems that this the whole concept of death and dying is more related, as I mentioned just a moment ago, to creatures that sort of have a greater understanding of a mind, can sense pain, and but we need to remember that the spiders themselves are such amazingly complex creatures that they really are a major problem and a greater problem from the theory of evolution because of their design. And so my view is that the spiders, the insects, bacteria, viruses, all played a role in maintaining a balance or an ecological system in nature that provided food and a lovely environment for the higher animals that and ourselves as humans, etc. So that's a view on the situation. Of course, when we get to heaven, we can ask God how the system works, but the overwhelming evidence is for creation, for an amazing designer. When we look at and investigate the design attributes, and spiders are a classic example of amazing design. So much complexity in a spider in terms of a design in such a small creature, with amazing properties, amazing engineering properties, and I think that spiders provide powerful evidence for a creator. We know through personal experience, through the biblical and through a whole lot of other evidence that it's a loving creator. And so the existence of poisonous spiders and so forth, it certainly raises an interesting questions perhaps we can't answer. But I think if I look at it in terms of, as Sir Albert Howard said, there has to be a balance in nature. And these insects, viruses, not so much viruses, bacteria replicate so rapidly they would soon take over the world, and yet they play essential functions. For example, the insects are essential in pollination of the flowers and plants and many seed plants, this sort of thing. And so they seem part of a system more as replicating sort of little robot, self-reproducing little robot creatures, as opposed to creatures that can have a mind and can enjoy pleasure and so forth. So anyway, that's my view there. But what I was wanting to talk about today, of course, is the overwhelming evidence for creation and a major problem for evolution in terms of the design of spiders, and bearing in mind as we look at all the attributes that spiders have, that these attributes had to have, according to the theory of evolution, arise by blind, random, chance mutations. And I think the evidence is so overwhelming. It's absolutely impossible for the DNA code by random changes to produce these creatures. So what is a spider? Spiders are arthropods, or animals with jointed appendages. And they have two main body regions and 4 pairs of walking legs or 8 legs. And they have silk glands in their abdomen. And most of them have about 8 eyes, and they have fangs, and they usually have in their tail end 6 spinnerets, structures on their abdomen from which they extrude this particular substance that we call silk. It's not the same as silkworm silk, but it's called a silk in that it's a strand of material that is used to make their webs. And, of course, they use these strands to make their webs, their egg sacs, and also material to wrap their prey. Now, the design of these spinnerets is quite detailed, and each spinneret has several tiny little spigots from which the silk is stored in the silk glands in a liquid form. And it comes out these little spigots. So the silk is pre-stored, liquid, and spins out. Now, when it's drawn out from the spinneret, and this is done by using one of its hind legs, it actually turns into a solid. But this is not the result of drying. Instead, the liquid actually solidifies because the tension of drawing out actually aligns the protein molecules into a parallel arrangement in which they bond together. So in other words, in the liquid they're stored in sort of all the molecules are all sort of aligned all differently, stored sort of mixed up. But this drawing out, because proteins are so long, draws them out in parallel and then they bond in parallel. So it's an amazing set of chemical reactions that occur. And for these compounds to have arisen by chance, and the whole mechanism to produce the silk is just so complex and just absolutely perfect that it could not arise by blind random mutations. Now, the different kinds of silk are highly complex protein molecules. So there's, I was reading, there's quite an interesting article on this actually that was published in the journal Creation, which is put out by creation.com in 2023. It's volume 45, number 4, and you can read about from pages 27 on. There's one species of spider, the Nephilia, that has a molecular weight of the silk has a molecular weight of about 40,000. It's an amazing molecules that produce these protein molecules are synthesised. And we've got to remember that to produce these molecules you need quite complex chemical reactions to synthesise these particular molecules. And very involved chemistry that could not arise by chance. And this is where I think when biologists and zoologists talk about the theory of evolution and that, my personal view is they just don't understand the complexity of the chemistry that's involved and the fact that this complex chemistry has to be written up in a coded instructions, and they have to believe that random blind changes to instructions can produce these amazing molecules that then work together. But not only do you have the chemicals that make up, for example, the silk, you've got the structures, the physical structures that hold the silk, that allow it to then be pushed out, and then the leg mechanism to draw it out, all this sort of thing. Now, of course, when we look at some of this, the spider silk, it's extremely thin. Some have a diameter less than 1,000th of a millimetre, and yet this material is twice as elastic as nylon and has a tensile strength, that is, how strong you have to pull it to break, that exceeds, in some cases, that of steel. And it can respond to a whole lot of different stresses. It's truly an amazing substance. Now, the other thing is, of course, that some spiders can have as many as 7 different types of silk glands, which open through particular kinds of spinets, such as, the female garden orb weaving spiders produce 7 different types of silk. So when we think of this again, we're looking at 7 different types of molecular structures when we talk about this. And so we're looking at 7 different types of chemical reactions to produce these types of silk, again, which all have to be encoded for in the instructions, which is the DNA code. It's interesting that the spinnerets as well can move in several different ways, lifting, lowering, twisting, and so they can synchronise the spinning. It's interesting that environmental clues can affect the behaviours and reflexes of spiders, and it seems that the way it weaves, it's where these structures are directed by environmental clues, not by the spider's mind. And so there's evidence that the particular complex instinctive reflex behaviours involved in spinning the webs are again programmed into their DNA. It's fascinating that the spiders all weave the same structure web, and so again this is more evidence that it's encoded in their DNA, because the baby spiders aren't trained by their parents. They hatch out of the eggs and race off, and yet orb-weaving spiders, most of us are probably familiar with seeing these in the garden, produce these beautiful circular webs which are produced in a particular pattern by the spiders. But again, the people that study this, they talk about the evolution of the web and this sort of thing. But one of the fascinating things is, of course, that we don't see new types of body parts evolving in spiders. And I'm very pleased that they don't evolve any bigger. I mean, just imagine a spider the size of an elephant. It'd be terrifying. And so it's interesting that they're constrained in this way. It's interesting that the variety of spiders. There's about 3,000 species of orb weaver spider, according to this article I was reading. And they fall into actually 2 major groups. And this is actually a barrier to the idea that one evolved from the other, or both from some ancestral group of orb weavers, because these 2 groups, their skill leads to this exact web design must have just happened to have evolved twice through blind chance mutations. And so one of the world-leading spider experts who published the book The Biology of Spiders, which is published by Oxford University Press back in 2011, says it's rather hard to imagine how such a complex structure could have come about, talking about the spider's web. And yet it's even more difficult to explain how an orb weaver web could develop in 2 different groups of spiders. So this is just one of the examples that, of course, evolutionists are recognising. But again, when we look at the codes, the instructions to make these webs are so complex. Overall, there's about 48,000 different species of spiders that display an enormous variety of webs. There's another book just devoted to them that's been published in 2020 by the University of Chicago Press. It's by W. Eberhard, and it's called Spider Webs, Behaviour, Function and Evolution. Of course, they're trying to explain it. But there's 816 pages of this book. And it's interesting, the range of spiders, like your jumping spiders. This is the largest spider family, called Salticidae, and comprises over 6,000 species of jumping spider. and their jumps are quite accurate, aided by excellent vision. And some Harvard researchers have recently started to develop microsensors for robots by copying the ingenious way a jumping spider's eyes deliberately use out of focus to precisely judge their leaps. You know, it's fascinating. And again, what we see is that scientists are going and looking at the design features that are there, teams of scientists, and working on trying to apply this to robots. And yet we have to believe that blind random mutations to a set of instructions could produce these eyes that all work. There's also cartwheeling spiders. These spiders tend to live on dunes, and they can flip their bodies sideways and cartwheel down sand dunes. And apparently they use this behaviour to escape predatory wasp. And they can travel at more than a metre per second, spinning at 20 revolutions per second. But again, this escaping the predatory wasp highlights this warfare between the insects that keeps them, and spiders and stuff, that keep this balance, ecological balance. Another fascinating aspect, there's a desert spider that they go on long nighttime travels looking for females, and yet they can return to their same burrows by a straight path. And so they can make an 800-metre round trip and still find their home burrow in the dark. And again, that was something you read about in the biology, in that book I mentioned earlier, The Biology of Spiders, published by Oxford University Press. Most spiders are solitary, of course. However, about 20 species gather in colonies. And there's one particular species called Anelosimus eximus that live peacefully in one web that can have a volume of 1,000 cubic metres. I find that hard to imagine. And so it'd be worth reading up a little bit more again. I wouldn't want to get into find myself in that particular web. Almost all spiders have venom glands, but only about 200 are dangerously poisonous to humans. And of course, here in Australia, we've got the funnel web spider, which is a very deadly spider. People have died from funnel web bites, and we get them at our place at certain times of the year. Maybe after a very heavy weather, we find that some of them can squeeze in under the door, and we find them wandering around in our laundry. Occasionally they've even made their way into our living room, and they look a scary spider. They're sort of shiny black and big, and I certainly don't like them. But it's quite interesting that they're not venomous to cats and dogs, but they're venomous to us. So, which is interesting. So there's amazing different aspects of spider and spider venom. But it's interesting, spider evolution is recognised as being a major problem. So according to the book The Biology of Spiders, published by Oxford University Press back in 2011, the author says, "I must admit, however, that our real knowledge of the evolutionary history of spiders is quite scanty, and hence to present any reliable pedigree is quite impossible. 90% of fossil spiders are from the tertiary period and thus relatively young. They resemble living families so closely that they provide hardly any clues as to how they supposedly evolved. Well, he used a different word, phylogeny, but I've just changed that to how they supposedly evolved. And so that's he writes that on page 327. In another place, he continues, there should be only one evolutionary history that is correct. However, to reconstruct the correct evolutionary pathway is quite difficult. Usually only one probable hypothesis can be formulated, and even those have to be constantly adjusted to new observations and insights so come to light. And so that's on page 334. And then a little bit further on page 335, he concludes, the evolutionary diagrams on tarantula and funnel web classification came out quite different when molecular analyses of the RNA genes had been used in comparison to those that are based on structural characters, and it is difficult to say which one is closer to the truth. So what they're saying there is when we look at the physical structures they get one evolutionary pathway. When they look at the RNA genes, they get a totally different pathway. And of course, if evolution had really occurred, we would have expected to see the same pattern indicated on both molecular and structural comparisons. So, of course, so we can see the complexity of spiders, these other major problems with trying to sort out their evolution, again point to the biblical creation account being the real explanation for spiders. And I think it's so important that we recognise that we have evidence for a loving Creator God, and it behoves us, each one, to get to know that God. The Bible clearly talks about how God wants to have a relationship with us. The Creator God wants to have a relationship with us. He came to earth and lived as Jesus Christ to show us the way. And this is so important. And again, the promise is that we won't die eternally. The promise is that God, if we choose to be with God, to get to know Him, after we've died, we will be raised again to live with Him. And that's why it's so important that we learn about God and seek to have that relationship with Him. And that's one of the purposes of these programs. So remember, if you want to re-listen to these talks, just Google 3abnaustralia.org.au, click on the radio button and look for Faith and Science and click on the listen button. You've been listening to Faith and Science. I'm Dr. John Ashton. Have a great day.
You've been listening to a production of 3ABN Australia Radio.